Hello student, my name is Mrs. Neeta Patil, Assistant Professor, Department of Mathematics, KIT's College of Engineering, Kolhapur. We have studied evaluation of double integral with given limits in Cartesian and polar coordinate system. But in some of the examples, we need to evaluate double integral over a given region. So in this video, we are going to study evaluation of double integral over a given region in Cartesian coordinate system. Now let us take the second example. Evaluate double integration y dx dy over the area bounded by x is equal to 0, y is equal to x square, x plus y is equal to in the first quadrant. Let us see the solution. Denote the given integral by the symbol I. So let I is equal to double integration y dx dy. Call this equation as equation number 1 and write down the given equation of curves. That is x is equal to 0, y is equal to x square, x plus y is equal to 2. Now we sketch these curves on xy coordinate system. So first equation of curve is x equal to 0. X equal to 0, it is the equation of y-axis. Y is equal to x square, it is the equation of parabola having the symmetry along y-axis, and x plus y is equal to 2, it is the equation of straight line. Now to get the point of intersection, means these 2 points A and this point, we solve the equation y is equal to x square and x plus y is equal to 2 simultaneously. So first of all, consider x plus y is equal to 2. Put y is equal to x square in above equation. We get x square plus x minus 2 is equal to 0. So this is a quadratic equation. You find out the factors of this equation. We get x plus 2 into x minus 1 is equal to 0. This implies x is equal to minus 2 or x is equal to 1. When x is equal to minus 2, you get the value of y is equal to 4. When x is equal to 1, you get y is equal to 1. So here we get the 2 point of intersection whose coordinates are 1, 1 and minus 2, 4. Now, after getting the point of intersection, the area bounded by these two curves and y-axis we have shaded by these red lines, and that region it is called as region of integration. So to get the limit of inner integral and outer integral in the region of integration, consider one strip PQ parallel to y-axis. Now in this region we consider strip parallel to y-axis. So limit of inner integral it is for the variable y and limit of outer integral it is for the variable x. Now to get the limit of inner integral, again consider the equation of curves at both end of the strip, means equation of curve at Q and equation of curve at P. So at Q, the equation of the curve is y is equal to x square. So y is equal to x square is the lower limit of inner integral, and upper end of the strip it is on the line x plus y is equal to 2. From this equation, write down y in terms of x. So we get y is equal to 2 minus x. So y is equal to 2 minus x is the upper limit of inner integral. So in this way we get the limit of inner integral as y is equal to x square to y is equal to 2 minus x. Now to get the limit of outer integral, we move the strip PQ from one end to other end in the region of integration. So if you move the strip PQ from origin to this point, then value of x, it varies from x is equal to 0 to x is equal to 1. So x is equal to 0 is the lower limit of outer integral and x is equal to 1 is the upper limit of outer integral. So we get limit of outer integral as x is equal to 0 to x is equal to 1. Now put the limits of inner integral and limits of outer integral in the equation 1. We get I is equal to double integration x is equal to 0 to 1, y is equal to x square to 2 minus x, y dx dy. As the limit of inner integral it is for the variable y, so we integrate the function first with respect to y and then with respect to x. So it is equal to integration 0 to 1. Take the integration of y with respect to y, we get y square upon 2, upper limit 2 minus x, lower limit x square. That is equal to 1 upon 2 integration 0 to 1, put y is equal to 2 minus x upper limit, we get 2 minus x square, minus put y is equal to x square lower limit, we get x is to 4 into dx. So it is equal to 1 upon 2, integrate this function with respect to x. So integration of first term 2 minus x square, it is 2 minus x cube upon minus 3. Here we are using the formula of x to n, as we know that integration of x to n is x to n plus 1 upon n plus 1. So it is equal to 1 upon 2. Now put x is equal to 1 upper limit, we get the first term minus 1 upon 3, second term 1 upon 5, then put x is equal to 0 lower limit. So when you put x is equal to 0 here, we get 8 upon 3 and the second function it becomes 0. After simplifying this bracket you get the term value 32 upon 15. Simplify, we get 16 upon 15. So this is the final answer for the given integral. Now let us consider the third example. Evaluate double integration x square plus y square dx dy over the area of triangle whose vertices are 0, 1, 1, 1, 1, 2. Let us see the solution. Denote this integral by the symbol I. So let I is equal to double integration x square plus y square dx dy. Call this equation as equation number 1. Write down the given vertices of triangle, that is 0, 1, 1, 1, 1, 2, and plot these points in xy coordinate system. So the point A whose coordinate are 0, 1, the point B whose coordinates are 1, 1, the point C whose coordinates are 1, 2. Now join every 2 points by a straight line. So we get the triangle ABC and the area under inside this triangle we have shaded by the red lines, and this area it is called as the region of integration. Now first of all we are finding the First of all, we are finding the equation of the line AC. So we get use the 2-point form. So we get the equation of line as y is equal to x plus 1. Now to get the limit of inner integral and limit of outer integral in the region of integration, consider one strip parallel to y-axis. To get the limit of inner integral, again consider the equation of curve at both ends of the strip. So the lower end of the strip, it is on the line AB, whose equation is y is equal to 1, and upper end of the strip, it is on the line AC, whose equation is x plus 1 is equal to y. So y is equal to x plus 1. It is the upper limit of inner integral. So here we get limit of inner integral y is equal to 1 to y is equal to x plus 1. Now to get the limit of outer integral, we move the strip PQ from point A to point B. So the value of x, it varies from x is equal to 0 to x is equal to 1. So these are the limits of outer integral. Now put the limits of inner integral and outer integral in equation number 1. We get I is equal to double integration x is equal to 0 to 1, y is equal to 1 to x plus 1, x square plus y square dx dy. As the limit of inner integral, it is a function of y, so we integrate the function first with respect to y, then with respect to x. So it is equal to integration 0 to 1. As we are taking the integration with respect to y, so x square is constant, keep as it is, and integration of dy is y plus integration of y square, it is y cube upon 3, upper limit x plus 1, lower limit is 1, dx is equal to integration 0 to 1. Now put y is equal to x plus 1, so we get x square into x plus 1 plus x plus 1 cube upon 3. Now you put y is equal to lower limit minus first term, you get x square, second term 1 upon 3 into dx. You simplify these terms, we get 1 plus 1 uh, 1 upon 3 x is to 4 plus x cube plus 3x square upon 2. Upper limit is 1, lower limit is 0. That is equal to 1 upon 3, 1 plus 1, 3 upon 2 is equal to 7 upon 6. So this is the final answer of this example. Now take the last example. Evaluate double integration over the region R x square dA, where R is the region in the first quadrant bounded by the hyperbola xy is equal to 16 and the lines y is equal to x, y is equal to 0 and x is equal to 8. First of all, denote this integral by the symbol I. So let I is equal to double integration over the region R x square dA. Here dA is equal to dx into dy. Call this as equation number 1. Now first write down the given equation of curves. Y is equal to x, y is equal to 0 and x is equal to 8 and xy is equal to 16. So sketch these curves in the on xy coordinate axis. So xy is equal to 16, it is the equation of a rectangular hyperbola. Y is equal to x, it is the equation of line passes through the origin. y is equal to 0, it is the equation of x-axis, and x is equal to 8, it is a straight line which is parallel to y-axis. Now the area bounded by these four curves that we have shaded by these red lines, and that region it is called as a region of integration. Now the line y is equal to x intersects the hyperbola xy is equal to 16 at the point C44, and the line x is equal to 8 intersect the hyperbola at the point B whose coordinates are 8, 2. Now if you see in the region of integration, here we have considered the two strips which are parallel to y-axis. So here why we are taking the two strips separately in the region of integration. So first strip we have considered on the in the left part of the region, and the second strip we have considered in the right part of the region. So what happened if you consider the strip, first strip, this strip, and consider the equation of the curves at both end, then lower end of the strip it is on x-axis and upper end of the strip it is on the line x is equal to y. Now if you move this strip and come to this point, and here the lower end of the strip it is again on x-axis, but upper end of the strip it is on the hyperbola whose equation is xy is equal to 16. Means throughout the region if you consider only single strip, then we cannot get the same limit for x or y. For that we divide this region into two sub-regions. To get that two sub-regions, through this point of intersection you draw a line perpendicular to y-axis and divide this whole region into the two sub-regions, first ODC and the second region it is DABC, and we have to evaluate this integral separately in the first region and in the second region. So let us denote the integral in the first region by the symbol I1 and integral in the second region by the symbol I2. Therefore we get I is equal to I1 plus I2. Call this equation as equation number 2. And now we are finding the limit of inner integral and outer integral. So consider a strip parallel to y-axis in the region ODC and find out the limit of inner integral. So as the strip is parallel to y-axis, the two ends of the strip, consider the equation of curves. So lower end of the strip it is on x-axis, so equation of x-axis is y is equal to 0. Upper end of the strip it is on the line x is equal to y, so we have to write down y is equal to x. As we consider the strip parallel to y-axis, so limit of inner integral it is for the variable y, so we get the limits of inner integral y is equal to 0 to y is equal to x. Now to get the limit of outer integral, we move this strip from origin to this point D. So when you move this strip along x-axis from origin to this point, then value of x varies from x is equal to 0 to x is equal to 4. So in this way we get I1 is equal to double integration x is equal to 0 to 4, y is equal to 0 to x square dy dx. It is equal to integration 0 to 4. Now As the limit of inner integral, it is for the variable y. So we integrate this function first with respect to y, then with respect to x. So it is equal to integration 0 to 4 integration of dy y upper limit x lower limit x 0 x square dx. It is equal to integration 0 to 4 replace y by upper limit x minus lower limit 0 x square dx. Now that is equal to integration 0 to 4 x cube dx. Integration of x cube, it is x is to 4 upon 4 upper limit 4 lower limit 0, it is equal to 1 upon 4. Put x is equal to 4 upper limit, we get 4 is to 4 lower limit, the function it becomes 0. So you get the value of I1 is equal to 64. Call this equation as equation 3. Now consider a strip parallel to y-axis in the region DABC. Now to get the limit of inner integral, again consider the equation of curves at both ends of the strip. So lower end of the strip, it is on x-axis. So equation of x-axis is y is equal to 0. This is the lower limit of inner integral, and upper end of the strip, it is on the hyperbola xy is equal to 16. From this equation write y in terms of x. So we get y is equal to 16 upon x. So this is a upper limit of inner integral. So limit of inner integral as y is equal to 0 to y is equal to 16 upon x. Now to get the limit of outer integral, in the region of integration we move this strip from the point D to point A. So when you move this strip from point D to point A, the value of x, it is varies from x is equal to 4 to x is equal to 8. So in this way we get the limit of outer integral x is equal to 4 to x is equal to 8. Now you put the limit of inner integral and outer integral in I2, we get double integration x is equal to 4 to 8, y is equal to 0 to 16 upon x, x square dy dx. As the limit of inner integral, it is for the variable y. So we integrate this function first with respect to y, then with respect to x. So it is equal to 4 integration 4 to a integration of dy x square dx, it is equal to 4 to 8 integration of dy is y upper limit 16 upon x lower limit 0 x square dx, it is equal to integration 4 to 8 16 upon x into x square dx. So one x get cancelled here, so it is equal to 16 integration 4 to 8 x dx, it is equal to 16 integration of x square upon 2 upper limit is 8 lower limit is 4, we get 8 into put x is equal to 8 upper limit, you get 64 minus x is equal to 4 16, simplify, we get the value of I2 is 384. Call this equation as equation number 4. Now from equations 2, 3, 4, we get I is equal to I1 plus I2, value of I1 64, value of I2 384. So you get the answer 448. So this is the answer for the given integral. Hope all of you understood the procedure and the examples over the given region. In the next video, we are going to study the evaluation of double integral over a given region in polar coordinate system. Thank you.